Hey there. Today, we delve into a secret that could have changed the course of World War II. A discovery that shattered German assumptions about American technology and industrial power. Imagine a tiny radio crystal worth 40 hours of German research, precision ground quartz that represented a leap in manufacturing, something Germans believed was impossible to mass produce at scale. What if the Allies' most advanced communication systems were so sophisticated, so precisely engineered, that they operated seamlessly in battle, while German equipment struggled with manual tuning and unreliable parts? Could a single captured American radio set, built with interchangeable modules and automatic frequency control, reveal a technological gap 5 to 10 years ahead of German designs? And if so, what did it say about the true strength behind Allied victories? In this video, we will trace how a small component uncovered a massive industrial revolution, one where mass production, standardization, and automation became the ultimate weapons. The question is, how did the Americans achieve such technological dominance, and what does it mean for the future of warfare? The answer begins right now, as we explore the incredible story behind the rise of American military electronics and its profound impact on the outcome of the war. On the 16th day of February in the year 1943, a momentous event unfolded that would challenge all assumptions held by German military strategists. Engineer Klaus Hermann, a seasoned expert in radio technology serving under the Wehrmacht, carefully grasped a metal case that had been sealed and secured through recent combat. The case contained a captured American radio device, a piece of enemy equipment that, at first glance, appeared ordinary but, in reality, held the potential to reveal startling truths. As Hermann unlocked the case, the slight trembling of his hand betrayed the significance he and his colleagues attached to this moment. Surrounding him, 5 of Germany's most skilled radio engineers leaned in with keen anticipation, eager to examine the contents of the equipment that their units had managed to seize during the recent intense engagement at Casarine Pass. This was no small feat. After 3 years of relentless propaganda insisting that American technology was inferior, mass-produced, cheaply assembled, and lacking the finesse of European engineering, the Germans believed they had the upper hand. Berlin's reports had consistently portrayed American devices as primitive, outdated, and reliant on untrained operators, backed by a perception that the industrial capacity of the United States could not possibly match the sophistication of German technology. However, the discovery of this radio set called all those assumptions into question. The equipment in question was an 508 Seychelles rupees model, a sophisticated piece of communication hardware pulled intact from a destroyed American M4 Sherman tank, which had fallen in the rugged mountains of Tunisia. The moment Hermann and his team examined the device, they realized that its construction, capabilities, and design far exceeded their expectations. Over the following 72 hours, their meticulous analysis would threaten to dismantle the entire foundation of German military intelligence regarding American industrial strength, technological advancement, and the strategic potential of Allied forces. The underlying mathematics of radio communications, complex and highly precise, began to unveil a truth far more disturbing than any battlefield loss. As the German engineers carefully disassembled and studied the captured equipment, they uncovered not merely a technological gap but an entire chasm of industrial disparity. This divide was so vast that it seemed to foretell Germany's eventual defeat, rooted not just in the battlefield but embedded in the very fabric of American mass production, crystals, automatic circuits, and standardized manufacturing processes that the Germans could never hope to replicate with their own industrial methods. The incident that led to this critical capture had begun 2 days earlier, on February 14, in the treacherous terrain of Casarine Pass. During a desperate counterattack, General Irwin R. Mills' forces, facing the inexperienced and overconfident American troops, achieved a tactical victory of their own. They pushed the United States Second Corps back by some 50 miles and managed to destroy over 100 American tanks in the process. Amidst the wreckage, German technical intelligence teams swiftly moved to gather intelligence, scouring the battlefield for weapons, documents, and equipment that could shed light on the capabilities of the Allies. Among those tasked with this crucial mission was Friedrich Weber, a commanding officer of a signals intelligence detachment attached to the 21st Panzer Division. Weber had standing orders to seize any American radio equipment that could be recovered intact, as such devices held vital clues to the Allied communications network. In a crater located east of the pass, his team discovered an abandoned Sherman tank, its turret shattered by a German 88mm gun, yet remarkably, its radio compartment had escaped damage. Inside this compartment, Weber's team made a remarkable find, not just one but two complete radio sets. The first was the 508 Seychelles rupees, a radio designed specifically for tank-to-tank communication, an essential tool for coordinating armored movements and battlefield tactics. Alongside it was an 510 Seychelles rupees receiver, a device capable of tuning into Allied signals at various frequencies. Both pieces of equipment were found in perfect condition. Their crystals, cables, and even the technical manuals were still securely mounted in their designated brackets, testament to the quality of American manufacturing. Recognizing the importance of this discovery, Weber immediately ordered that the equipment be transported without delay to the nearest German technical testing station. He understood that analyzing these radios could provide invaluable intelligence about American communication strategies, technological sophistication, and perhaps even reveal how the Allies maintained such effective coordination across vast distances. On the following day, February 16, the radios arrived at a specialized facility designated as Technical Testing Station 12. Here, the German engineers and scientists would begin the painstaking process of examining, testing, and decoding the equipment. They aimed to understand not only how these radios functioned but also what insights they might offer about American industrial capacity, an essential piece of intelligence that could influence the course of the war. What they uncovered in those next few hours would fundamentally alter the perception of American technological prowess. It became clear that the United States had developed communication systems so advanced and so efficiently mass-produced that the Germans could only regard them with a mixture of awe and trepidation. The implications extended far beyond the battlefield, hidden within an underground complex beneath the city of Tunis. There was a clandestine facility designed to house some of the most advanced radio engineering expertise that Germany had ever cultivated. This secret installation was manned by a team of highly skilled radio engineers, men who had previously been responsible for designing the communication systems used by the Wehrmacht. Their work had been instrumental in establishing Germany's military radio infrastructure, and now they found themselves working in a covert operation far from the front lines. Leading this team was Oberingenieur Klaus Hermann, a former chief designer at Telefunken, renowned for his meticulous craftsmanship and technical mastery. Alongside him were specialists in various fields, including frequency generation, circuit design, manufacturing techniques, and signals intelligence, each bringing their own expertise to the inspection of these enigmatic devices. Together, they embarked on a thorough examination of the equipment they had discovered. The first step in their investigation was an external inspection of the radios. Herman observed that the American models were encased in heavy-duty steel housings painted in a dull olive drab color, with rubber gaskets meticulously sealing every seam and connector to prevent the ingress of water, dust, and other environmental hazards. In his initial report, Herman remarked that the overall construction quality surpassed anything he had encountered in German military equipment, an indication of the high standards applied by the American engineers. When they finally removed the protective covers, the true nature of these radios became evident. Inside, everything was arranged with a level of standardization and modularity that suggested mass production rather than individual craftsmanship. Each component was manufactured to exact specifications, and every part was interchangeable, with no signs of manual adjustments or custom tuning. There were no technician marks indicating localized modifications or individual calibrations, which suggested the entire set was designed for rapid assembly by semi-skilled workers. The equipment's uniformity pointed to a manufacturing process scalable across continents, capable of producing millions of units rapidly and efficiently. Lieutenant Hans Schreiber, a specialist knowledgeable in frequency control, took particular interest in the crystal units that determined the radio's operating frequencies. His expectation was to find simple, inexpensive crystals, perhaps even salvaged civilian components, given the apparent mass production. Instead, he uncovered a surprise: precision quartz crystal oscillators, each carefully ground to tolerances measured in parts per million. These crystals were hermetically sealed within metal holders, their specifications requiring laboratory-grade precision, a feat that would have demanded weeks of meticulous work in Germany's own facilities. The SC County Route 508 model contained 10 crystal-controlled channels, each crystal individually packaged, fully interchangeable, and clearly marked with their exact frequencies. Schreiber counted the crystals twice, unable to believe what he was seeing. In Germany, crystal-controlled radios were typically reserved for high-command units and aircraft, where the scarcity and expense of precision crystals justified their use. Yet here, in a standard American tank radio, 10 such crystals were installed as casually as light bulbs in a household fixture. The implications were staggering. Carefully removing one crystal for closer examination under magnification, Schreiber noted that the quartz was flawless, free of any defects, and that the electrodes were perfectly aligned. The frequency markings on the crystals were exact and precise, reflecting high manufacturing standards. This single crystal, he realized, would have cost more than the entire German Fug 5 radio set in both materials and labor. The Americans, however, had installed 10 of these sophisticated crystals in each tank radio, and at that moment, the team was aware that thousands of Sherman tanks had already been equipped with these devices. Further analysis revealed even more unsettling details. Unlike the German radios, which employed amplitude modulation, or AM, the American models operated on frequency modulation, or FM. While FM was theoretically superior, offering clearer, static-free communication and better resistance to interference, the technology required far more complex circuits and extremely precise frequency control. Such sophistication pointed to a strategic advantage that the Americans had developed, one that could potentially revolutionize battlefield communications. This discovery suggested that the American forces had invested heavily in the development and mass production of advanced radio systems capable of operating with high fidelity and resilience in combat conditions. The detailed examination of these units provided a glimpse into a technological edge that could significantly influence the outcome of military engagements, revealing a level of engineering excellence that surpassed expectations and underscored the importance of electronic warfare in the modern battlefield. Control was a concept long considered by German engineers, especially in the context of military communications. They had initially evaluated frequency modulation, or FM, as a promising technology for battlefield radios. However, after thorough analysis, they had dismissed it as too costly and too complex to be practical for field deployment. The intricacies involved in manufacturing FM components and the detailed tuning procedures needed for operation made it unsuitable for the rapid, rugged conditions of wartime use. Yet, the reality in the field told a different story. Suddenly, there was an FM radio, mass-produced, robust, and installed in tanks driven by young, eager American soldiers. The circuit boards inside these devices revealed a sophisticated feature: automatic frequency control circuits, known as AFC. These circuits ensured that the radio remained locked onto a chosen frequency without requiring constant manual adjustments. In stark contrast, the German radios were far less advanced in this aspect. Operators of the German equipment had to continuously retune their radios to compensate for various factors such as temperature fluctuations, component aging, and changes in power supply voltage. This manual tuning was a tedious process, demanding constant attention and skill. Meanwhile, the American radios, it appeared, could self-tune, adjusting automatically to maintain a steady signal. Sherman, a senior officer on the team, began drafting his initial report to the German High Command in Berlin. The words came slowly and carefully, as each sentence challenged the established propaganda and intelligence assessments they had long believed. He stated that the captured American radio represented a level of technological sophistication that Germany was incapable of matching at that time. The components used in these radios were manufactured with an extraordinary degree of precision, requiring specialized factories equipped with advanced machinery, skilled workers, and rigorous quality control processes, resources that the German Reich simply lacked. More unsettling still, it was evident that this radio was not a prototype or limited-run model. Its design and assembly clearly pointed toward a mass manufacturing process. Every detail of its construction screamed efficiency and scale. Over the next 3 days, the team systematically tested every function of the captured radio units. They connected the devices to power supplies, antenna systems, and a variety of test instruments, all housed within the underground laboratory. With each successive test, their unease grew stronger. They discovered that the 508 Seychelles rupees transmitter could produce a consistent 25-watt FM signal across 10 selectable channels. The switching mechanism that enabled channel selection was elegant, reliable, simple to operate, and requiring no specialized knowledge. A tank commander need only rotate a knob to choose a preset crystal. The radio would then automatically switch frequencies, retune its circuits, and maintain a perfect transmission quality. This was a stark contrast to German radios, where changing frequencies involved manually adjusting multiple controls, replacing coils, and spending several minutes retuning the device. The American system was a marvel of simplicity and automation, designed to be operated easily in the chaos of battlefield conditions. Range tests confirmed their suspicions further. Using a captured American whip antenna, the team managed to establish communication with a monitoring station located 20 kilometers away. The FM signals traveled clearly, free of the static, fading, and interference that so often degraded German AM communications. Even when electrical noise was artificially introduced, such as from a tank engine running nearby, the FM receiver's limiter circuits effectively stripped away the interference. The result was a clean audio signal, one that German operators could only dream of achieving with their outdated equipment. Lieutenant Schreiber, one of the team's engineers, focused intently on the crystal oscillator circuits. He traced every component meticulously, measured voltages with precision, and documented his findings in extensive detail. His examination confirmed his worst fears. The crystal control system was not merely advanced but fundamentally impossible for German manufacturing capabilities to replicate at that time. Each crystal oscillator required a precisely cut quartz plate, ground with extraordinary accuracy. This process involved generating a crystal with an exact resonance frequency, one that maintained stability over a broad range of conditions. The technological sophistication and manufacturing expertise needed to produce such crystals were beyond the reach of the German industrial infrastructure in the war years, further deepening the sense of technological disparity between the two sides. The manufacturing process for these specialized crystals involved measuring their dimensions with extraordinary precision, down to the thousandth of a millimeter. Once crafted, the crystals were carefully mounted within vacuum-sealed or gas-filled holders, with electrode spacing that was controlled to such tight tolerances that even German factories, known for their meticulous standards, could not reliably reproduce such precision on a large scale. These meticulous measurements and mounting procedures were critical because they ensured the crystal's stability and performance in their intended applications. To achieve optimal frequency stability across a wide temperature range, from as low as -40 degrees Celsius to as high as 60 degrees Celsius, advanced temperature compensation circuits were incorporated into the design. Such circuits adjusted the crystal's characteristics dynamically, preventing drift and ensuring consistent operation regardless of environmental fluctuations. Strikingly, a researcher named Schreiber estimated that manufacturing a single crystal to American specifications, which required tight tolerances and precise assembly, would consume around 40 hours of highly skilled technician labor in German laboratories. This level of craftsmanship meant that the Americans, who had already installed hundreds of these crystals into a variety of military radios, could produce them at an astonishing scale. Considering that hundreds of thousands of Sherman tanks had already rolled off production lines, many equipped with these radios, and that similar radio systems were installed in numerous American jeeps, trucks, and command vehicles, it became clear that the United States was producing millions of these high-precision crystals annually. This raised a fundamental question of strategic importance. How were the Americans able to supply such an enormous volume of crystals when their production relied on highly skilled technicians, whose labor was both time-consuming and costly? The answer, provided by informed sources, was even more unsettling. Instead of depending on a small cadre of expert technicians, the Americans had effectively industrialized the entire process. They had established new factories in cities with names like Chicago, Newark, and Fort Wayne, which employed thousands of semi-skilled workers, predominantly women, operating specialized grinding machinery designed for automated crystal production. The precision measurements necessary to ensure the crystal's performance were carried out not by skilled technicians but through optical comparators and frequency counters, devices that could quickly verify the critical parameters without requiring expert intervention. Quality control shifted from meticulous individual inspections to statistical sampling methods. Instead of testing each crystal, random samples from production batches were analyzed, allowing for rapid throughput while maintaining consistent quality. This transformation represented a significant leap. What had once been considered a delicate laboratory art, crafting and measuring these tiny resonators, had been converted into a streamlined, industrial manufacturing process. Further examination of the radio receiver components revealed even more advanced technological approaches. The superheterodyne circuit design was similar to that used in German radios, but the quality of the American components surpassed their German counterparts in every measurable aspect. Vacuum tubes, for instance, were manufactured within tighter tolerances, and their characteristics were precisely matched to circuit requirements, resulting in better stability and performance. Capacitors and resistors also featured stability ratings that German parts could not match, ensuring the reliability of the entire system. The design philosophy extended to ease of maintenance and rapid repair. The entire receiver was engineered so that most adjustments could be made by semi-skilled technicians using straightforward test equipment, rather than requiring the expertise of highly trained radio engineers. This approach greatly simplified field repairs, which was crucial in wartime conditions. One of the most revolutionary features was the modular construction of the radios. Each major subsystem, whether the transmitter, receiver, power supply, or control unit, consisted of a separate, interchangeable module. If a particular component failed, a crew could quickly remove the defective module and replace it with a ready spare, doing so in mere minutes and without the need for tools or advanced technical knowledge. Damaged modules could then be shipped back to depot facilities for repair or disposal, creating a streamlined supply chain for replacements. This modular system demanded a vast industrial capacity to produce large quantities of spare modules, but it offered significant tactical advantages. American tanks could maintain their communication links under conditions that would have left German vehicles completely silent for days while technicians attempted repairs in the field. The ability to swiftly swap out faulty modules helped ensure continuous operational capability even in the midst of intense combat. Accompanying these sophisticated radios were technical manuals, well illustrated, printed on high-quality paper, with clear diagrams and straightforward instructions. Designed with simplicity in mind, these manuals assumed that operators had only minimal technical training, enabling even less experienced personnel to perform basic maintenance and troubleshooting. This democratization of technical knowledge further contributed to the resilience and responsiveness of American armored units, allowing them to keep communications systems operational under the most demanding circumstances. Operating procedures were simplified into clear, numbered steps, making complex tasks accessible to ordinary soldiers. Troubleshooting guides relied on decision trees, logical flowcharts that any soldier could follow with minimal training. Maintenance instructions were precisely detailed, specifying exact intervals for replacing components rather than leaving it to the operator's judgment. This approach reflected a broader philosophy that prioritized simplicity and standardization over individual technical expertise. Sherman came to the realization that these manuals revealed as much about American industrial and military thinking as they did about the radios themselves. The Americans had deliberately designed equipment that did not depend on the technical skills of its operators. Instead of training every radio operator to master electronics, an expensive and time-consuming process, they had created machinery that could be operated and maintained by any reasonably intelligent soldier, following straightforward procedures. This strategy demanded the development of more advanced, robust equipment, but it effectively solved the critical military challenge of maintaining reliable communications in the chaos of combat. In stark contrast, German radios required highly skilled operators with a deep understanding of radio theory. These specialists could perform field repairs, had the technical judgment to troubleshoot and fix temperamental devices, and needed months of intensive training coupled with years of experience to become proficient. Such operators were invaluable assets whose loss often rendered the equipment they managed useless to their successors. By the end of the third day of the examination, the team had thoroughly documented every circuit, measured each component, and tested every function of the captured American radios. Their detailed report, submitted to the High Command of Wehrmacht, stretched over 200 pages and was complemented by photographs, circuit diagrams, and detailed specifications of each component. The findings were nothing short of shocking. The report's conclusions laid bare the technological gap. American radio technology was estimated to be 5 to 10 years ahead of German equipment in several crucial areas. Features like frequency modulation, crystal control, automatic frequency adjustment circuits, and modular construction represented fundamental innovations that could not be countered simply through tactical superiority or operator expertise. More significantly, American radio sets were engineered from the ground up with mass production in mind. Every aspect of their design embodied an industrial approach that Germany, with its more traditional, less flexible manufacturing methods, simply could not replicate. Herman's analysis estimated that Germany would need to establish at least 30 new specialized factories, train 50,000 additional workers, and allocate resources equivalent to the entire annual budget of the Luftwaffe just to match American radio production capabilities. Even with such an effort, the supply of critical raw materials, particularly high-quality quartz crystals and rare elements necessary for precision components, was insufficient. These materials were scarce, and wartime shortages made their acquisition even more difficult. The verdict was clear and unavoidable. American industrial capacity had conferred a decisive technological advantage in the field of communications. This superiority threatened to tilt the balance of power in favor of the Allies, making military victory in this domain increasingly unlikely for Germany. The report was delivered to Berlin on February 25, 1943, and was classified as most secret. It was circulated among only a select few senior officers within Wehrmacht High Command and the Reich Ministry of Armaments. The reaction was conspicuously silent. No immediate orders were issued to construct new factories, nor were any rapid development programs launched. The implications of the report were too overwhelming to face openly. Acknowledging the gap would mean admitting a significant setback in the technological race. Yet, despite the silence at the top, the work of Technical Testing Station 12 was only just beginning. Over the following months, more American equipment continued to fall into German hands through various captures, each one providing further insights and data that would shape the ongoing assessments of American technological progress. Every new piece of equipment that the Germans managed to analyze added to their understanding of how far ahead the Allies' radio technology was, and how urgent it was for them to find ways to bridge the widening gap. In the midst of World War II, the United States demonstrated a remarkable leap forward in military technology and communication capabilities, showcasing innovations that underscored their technological and industrial superiority on the global stage. Among these advancements was the SCR508 radio, famously known as the backpack walkie-talkie, which represented a groundbreaking leap in portable communication technology. This device incorporated FM transmission technology, a significant innovation at the time, and was so compact that it weighed only about 18 pounds, making it highly practical for field use. Despite its lightweight design, the SCR508 provided reliable communication links over distances reaching up to 5 kilometers, a feat that was notably superior to comparable German equipment. In comparison, German portable radios capable of similar ranges were considerably heavier, often exceeding 40 pounds, and required the addition of external battery packs that added another 20 pounds or more to the overall weight. These cumbersome setups made German portable radio operations less flexible and more challenging to deploy quickly in the field. An extraordinary piece of evidence of American innovation was the SCR-299, which was captured during operations in Sicily in July of 1943. This device astonished the examining team with its capabilities, as it was a mobile long-range communication station installed within a truck, complete with an integrated power generator. The transmitter of this station could produce 350 watts of power across a frequency range stretching from 2 to 18 MHz, all while maintaining crystal-controlled frequency stability, which allowed for rapid, precise frequency changes, often within minutes rather than hours. The accompanying receiver of the -299 Seychelles rupees employed a heliaccordion design featuring 15 vacuum tubes, multiple conversion stages, and a crystal filter aimed at enhancing selectivity and reducing interference. While the Germans had similar long-range communication systems, their equivalents were predominantly fixed installations, requiring enormous, building-sized antenna arrays and dedicated power sources, making them cumbersome and inflexible. In stark contrast, the Americans managed to package comparable capabilities into mobile vehicles capable of being driven virtually anywhere and set up within an hour, a testament to their emphasis on mobility and rapid deployment. This pattern repeated itself consistently across various captured equipment. American radio technology was notably designed for ease of use, requiring minimal training for operators, which made mass production feasible by semi-skilled workers. Maintenance procedures were simplified, enabling quick repairs through straightforward instructions. Conversely, German communication equipment demanded highly skilled operators, meticulous hand assembly by trained technicians, and field repairs conducted by electronics specialists, restricting its deployment flexibility. Such a disparity in design philosophies meant that the American approach was inherently scalable, capable of supporting the production and widespread deployment of millions of units across the globe, whereas the German methodology was limited to specialized, fixed installations. As the war progressed, technical intelligence reports from campaigns in Tunisia, Sicily, and later Italy painted a detailed picture of this disparity, not merely revealing information about individual radio sets but illustrating a comprehensive communications philosophy. American forces relied on an interconnected hierarchy of radio networks that maintained continuous contact from the squad level all the way up to theater command. For instance, platoons carried -536 Seychelles rupees portable radios, often referred to as handy-talkies, enabling immediate local communication. Companies were equipped with -300 Seychelles rupees backpack radios for more extensive range communications. Battalions operated vehicle-mounted sets such as the -508 Seychelles rupees and -608 Seychelles rupees, providing long-range links, while regiments employed even more powerful equipment like the -193 Seychelles rupees and -299 Seychelles rupees long-range systems. This layered structure created a robust web of connectivity that allowed seamless communication across different levels of command, a feat that German forces could not replicate with their less integrated systems. More critically, the American radios were built to be fully compatible with one another, using standardized frequency systems and interoperable equipment. For example, a forward observer armed with an -300 Seychelles rupees could effectively coordinate with an artillery battalion stationed 20 kilometers away by using an SCR508, because both sets operated on FM with crystal-controlled frequencies, ensuring stable, interference-free communication. In stark contrast, German forces relied on multiple incompatible radio systems, each operating on different frequencies, modulation types, and requiring distinct operational procedures. This fragmentation hampered effective coordination and limited the flexibility of their communications network. By the summer of 1943, signals intelligence gathered from various campaigns had documented the existence of over 50 different types of American military radios, ranging from small handheld transceivers to airborne command units. Intelligence estimates, derived from analyzing captured serial numbers and other sources, suggested that American manufacturing facilities were producing in excess of 100,000 military radios each month. This prolific production underlined the scale and efficiency of American military industry, allowing them to equip their forces with a comprehensive, interoperable communications infrastructure that was both sophisticated and adaptable. Such technological dominance and logistical capability played a crucial role in maintaining the operational flexibility and strategic advantage of Allied forces throughout the conflict, ultimately contributing significantly to their success on the battlefield. At the height of their production efforts, American factories managed to churn out approximately 15,000 units each month, an impressive feat of industrial scale and efficiency. This colossal output was driven by an integrated and highly standardized manufacturing process that facilitated rapid assembly and repair across a variety of radio types. Recognizing the importance of understanding their adversary's technological backbone, examination teams began meticulously analyzing the American manufacturing documentation that had been captured. These documents, including detailed technical orders, comprehensive parts lists, and extensive maintenance manuals, shed light on the intricate infrastructure that supported American radio equipment. One of the most notable features of this infrastructure was the remarkable standardization of components throughout various models. For instance, vacuum tubes, an essential element in radio electronics, were manufactured with common base configurations, enabling ease of replacement and interchangeability. Similarly, crystals, which served as frequency stabilizers, adhered to standard holder designs, simplifying their production and installation. Even the smaller, often overlooked parts such as screws, nuts, and bolts, followed unified thread standards that allowed parts to be swapped between different radio types effortlessly. This level of standardization meant that American factories could switch production lines from one model to another with minimal retooling, sometimes just by replacing a few fixtures or adjusting a handful of component types. The flexibility of this system was exemplified by the ability of a plant producing 508 Seychelles rupees transmitters to quickly pivot and begin manufacturing 608 Seychelles rupees units. Achieving such a transition required only minor adjustments, such as changing specific fixtures or substituting certain components. Moreover, many parts designed for one radio type could often be salvaged and repurposed to repair others, further enhancing the efficiency and resilience of the American military electronics industry. The entire production apparatus was deliberately designed for both scalability and adaptability, ensuring that wartime demands could be met swiftly and efficiently. In stark contrast, German manufacturing practices adhered to a much more specialized approach. Each piece of equipment was built with custom components tailored explicitly for its intended model. For example, the FUG-5 tank radio shared virtually no parts with the FUG-10 aircraft radio, despite their similar electrical functions. This meant that even though both devices performed comparable roles, they required entirely separate production lines, unique testing equipment, and dedicated inventories of spare parts, an approach that significantly hampered flexibility and response times. Altering production priorities in Germany entailed lengthy periods, often multiple months, of retooling machinery and retraining personnel, which slowed the ability to adapt to new demands or produce alternative models. By the autumn of 1943, the German engineer Sherman, working for Oberg, had been transferred to a larger and more strategic technical intelligence facility located in northern Italy. His role increasingly shifted from a focus solely on analyzing individual equipment designs to conducting comprehensive assessments of American manufacturing methodologies. Over time, his reports to Berlin evolved from technical evaluations of radio circuitry to broader strategic warnings about the industrial capacity of the United States. Sherman documented the rapid and explosive growth of the American electronics industry, highlighting how their industrial base had become a formidable force. American companies such as Galvin Manufacturing, which would later be known as Motorola, had undergone a remarkable transformation, from small operations producing consumer radios to massive military contractors capable of fulfilling large-scale wartime demands. Another notable enterprise, Helicrafters, originally focused on amateur radio equipment, was now producing highly sophisticated military receivers in quantities that vastly exceeded the total German radio output. This shift underscored the scale and efficiency of the American electronics industry during the war. The Western Electric Company, serving as the manufacturing division of the Bell telephone system, operated numerous factories employing tens of thousands of workers. These facilities produced a wide array of electronic components, including crystals, vacuum tubes, and entire radio sets. Remarkably, prior to 1941, these companies had not been major military suppliers. Their transformation into integral parts of the war effort was rapid and comprehensive. Within less than 2 years, the Americans had established a robust military electronics industry by converting civilian factories, deploying extensive training programs for new workers, and applying mass production techniques that had been perfected in the automotive and consumer appliance sectors. For example, engineers in Detroit adapted the highly efficient assembly lines originally designed for automobile manufacturing to produce radios and electronic components. These production lines operated with the same precision and speed, turning out thousands of units per week with minimal delays. Meanwhile, the German radio industry remained largely rooted in the organizational structures of the 1920s, concentrated in cities like Berlin, Munich, and Hamburg. Smaller manufacturers, often composed of skilled craftsmen, produced specialized equipment in relatively limited quantities, typically measured in hundreds per month rather than thousands per week. Their approach emphasized quality control through meticulous individual inspection and manual adjustments rather than statistical process control, which was a hallmark of American mass production. This traditional, craft-oriented methodology limited their ability to scale up rapidly in response to wartime needs, contrasting sharply with the American industry's dynamic and flexible manufacturing system. Process control and quality assurance stood at the core of American radio manufacturing efficiency during this period. The United States had made remarkable strides in automating testing procedures, which significantly boosted production speed and reliability. Sherman's December of 1943 report to the Reich Ministry of Armaments, titled "The American Radio Industry," offered an extensive examination of America's industrial capabilities and the strategic implications stemming from these technological strengths. The report meticulously documented American electronics production in staggering detail, revealing that the annual output of American industry was sufficient to produce in 1 year what would have taken Germany 2 decades to manufacture under its own conditions. This vast disparity was not merely a matter of technological advancement. It extended into industrial scale, organizational efficiency, and underlying philosophical approaches to manufacturing. The report estimated that American factories possessed the capacity to produce enough military radios to equip 1,000 divisions, though, in reality, the United States fielded approximately 90 divisions at that time. The surplus manufacturing capacity translated into an almost unlimited supply of replacement equipment for American forces. Unlike German units, which meticulously preserved and rationed every radio, American soldiers received ready replacements. Damaged radios in American units were discarded and replaced rather than repaired in the field. Outdated models were phased out systematically and sent to training units, while the newest, most advanced designs were introduced continuously. These modern radios were not mere prototypes, they were mass-produced, distributed across entire theaters of operation, ensuring widespread availability and uniformity. In contrast, German forces operated under strict resource conservation principles. Every radio was carefully maintained, with field technicians performing repairs under combat conditions. When a radio was damaged, technicians often resorted to cannibalizing parts from other units to keep the remaining equipment operational. Replacement radios arrived irregularly and in limited quantities, further complicating maintenance efforts. The Germans faced a significant challenge in updating their equipment, as retooling factories to produce newer designs would inevitably reduce the output of existing models, creating a strategic dilemma. This challenge was compounded by the fact that WWII, the German radio manufacturer, operated both older models from the early 1930s alongside newer equipment, resulting in a maintenance nightmare and adding to training difficulties for German technicians. A particularly critical bottleneck for German radio operations was the supply of precision crystals, essential components for frequency stability. By late 1943, German quartermasters estimated a need for 5 million crystals to sustain existing radio equipment and planned upgrades. The domestic capacity for crystal production was approximately 200,000 units per year, a figure vastly insufficient to meet wartime demands. Even with enormous resource allocation, it would take over a decade for Germany to produce the required 5 million crystals. Meanwhile, American crystal manufacturing had advanced beyond scarcity. Intelligence reports indicated that the United States was producing around 30 million crystals annually. American firms had secured deposits in Brazil, exploited mining operations in Arkansas, and undertook synthetic crystal growing experiments, methods that allowed for large-scale, high-quality production. American crystals were not only plentiful but also of superior quality, characterized by frequency stabilities that German laboratories could scarcely measure, let alone replicate. Further insights into the industrial gap came from examining captured American test equipment. American radio factories employed highly sophisticated automated test sets that could measure frequency, power output, modulation quality, and sensitivity within seconds. These testing instruments were themselves complex electronic devices, produced in large quantities so that each station along the assembly line had its dedicated testing apparatus. Such automation greatly increased throughput and ensured consistent quality. Conversely, German factories relied on manual testing procedures requiring skilled technicians and several minutes per unit. The process was slower, less consistent, and more labor-intensive. A single captured American test device, a signal generator produced by a measurements corporation, became a highly valued prize for the German technical testing facility. This instrument exemplified the technological edge of American manufacturing. It could generate precise signals for calibration and testing with remarkable speed and accuracy, facilitating rapid quality control that was simply unattainable with German manual methods. In summary, the disparity in process control, testing automation, and industrial capacity between the United States and Germany was profound. The American approach, characterized by mass production, automation, and extensive resource acquisition, created a formidable strategic advantage, while German efforts were hampered by resource shortages, manual procedures, and outdated infrastructure. This difference in industrial strength played a crucial role in shaping the technological and operational landscape of wartime radio communications. By the time early 2014 had arrived, it was painfully evident through meticulous intelligence gathering that the technological edge held by American military communication systems was not merely significant but utterly unrivaled and continuously expanding. The meticulous efforts to understand and analyze American radio and radar technology revealed a stark reality. The United States had achieved an extraordinary level of sophistication and manufacturing prowess in this domain, leaving their adversaries far behind. The construction of American communication devices was fundamentally different from their German counterparts, which often required extensive and expensive laboratory setups. For instance, a typical American radio apparatus, precisely calibrated across the entire radio frequency spectrum, could be assembled at a cost of roughly $300. In stark contrast, equivalent German equipment demanded a sprawling laboratory filled with numerous oscillators, attenuators, and frequency meters. Tools that not only cost thousands of Reichsmarks but also necessitated continuous calibration efforts by skilled engineers. This disparity highlighted the technological chasm that was rapidly widening in favor of the Americans. By the onset of 1944, the intelligence reports conveyed a disturbing yet unmistakable message. American dominance in communications technology was absolute, irreversible, and advancing at an unprecedented pace. Each passing month saw American factories churning out more radio units than Germany had in its entire military inventory, illustrating an industrial revolution in military communications that the Germans could scarcely hope to match. Every captured piece of equipment from the front lines underscored this trend, each new example revealing subtle yet consistent improvements, refined designs, and manufacturing techniques that showcased an industrial and technological sophistication beyond German capabilities. This technological superiority became even more apparent with the deployment of American radar systems in late 1943 and early 1944. Radar, a revolutionary leap forward in radio technology, had been pushed to its very limits with the advent of microwave frequencies, pulse modulation techniques, and advanced signal processing algorithms. The Americans, employing these innovations on a mass scale, were producing radar units for ships, aircraft, and ground-based installations with a level of industrial efficiency that matched their production of voice radios. One such example, a captured 584 Seychelles rupees fire control radar examined in March of 1944, demonstrated capabilities that German radar scientists had only theorized about, an indicator of just how far ahead the Americans had advanced. This particular radar operated at an incredibly high frequency of 3000 MHz, utilizing a precision tracking mount with automatic follow circuits. Its accuracy was sufficient to enable anti-aircraft guns to destroy enemy aircraft with devastating precision and effectiveness. Weighing over 10,000 pounds, the 584 Seychelles rupees required a dedicated vehicle to transport and operate it. Despite its size and complexity, American factories were mass-producing these units in the hundreds, reflecting a well-organized and highly efficient industrial system. German radar development, however, was still focused on long-wave systems operating below 1000 MHz, primarily because German industry lacked the capability to produce the specialized vacuum tubes necessary for higher frequency operation. The magnetron tubes used in American microwave radar demanded precision machining, exotic materials, and manufacturing processes, resources and techniques that German industry did not possess at the time. Even when German scientists designed microwave radar systems theoretically, the components needed simply did not exist within their industrial capacity, rendering such designs impossible to realize in practice. Throughout 1944, The systematic examination of captured American radar equipment continued as Allied forces advanced through Italy and prepared for the invasion of France. Every new piece uncovered added to the mounting body of evidence underscoring American technological superiority. Improvements in radio equipment persisted regularly, with each new model surpassing its predecessors. For example, the 694 Seychelles rupees, introduced in mid-1944, featured frequency modulation capabilities that enhanced tank communications range and reliability. Similarly, the 619 Seychelles rupees aircraft radio offered hundreds of crystal-controlled channels and near-instantaneous frequency switching, greatly improving operational flexibility and security. Most notably, the reliability of American radio and radar equipment continually improved over time. Initial models, such as the early production 300 Seychelles rupees radios, occasionally faced issues related to moisture ingress and unreliable battery contacts. However, captured examples from late 1944 displayed significant modifications, redesigned cases, improved sealing techniques, and enhanced components, all aimed at ensuring greater durability and operational consistency. These ongoing upgrades and innovations underscored a relentless drive toward perfection in American military communications technology, a drive that continually pushed the boundaries of what was possible and left German engineers struggling to keep pace with the rapid pace of American technological advancements. Throughout the course of the war, the United States made significant technological advancements in radio communication equipment, actively designing and producing circuits that effectively addressed and eliminated many of the persistent issues plaguing earlier models. These innovations weren't just about building new devices, they represented an ongoing process of refinement driven by real-world battlefield experience, with lessons learned directly integrated into manufacturing practices. This continuous improvement ensured that American radio systems maintained high reliability and performance under the toughest conditions. In stark contrast, German equipment, which once had been considered advanced, frequently declined in quality over time. As the war dragged on, various factors contributed to this decline. Material shortages began forcing the substitution of inferior components, which compromised the overall durability and efficiency of their radios. Skilled technicians and engineers, who would otherwise have maintained high standards, were increasingly diverted to combat duties, leaving less experienced personnel to handle repairs and assembly. Consequently, quality control measures suffered, with factories prioritizing rapid production and large quantities over the reliability and longevity of each device. The consequences of these deteriorations were visibly apparent on the battlefield. Radios, which ideally would have remained operational for many years, started failing after only a few months of active service. By the time the Allied forces launched the Normandy invasion in June of 1944, German military intelligence had already compiled comprehensive data demonstrating the stark disparity in communications capabilities. The Allies had successfully established a formidable communications network that outstripped the Germans' capabilities in both scope and reliability. In terms of radio inventory, the Allies had equipped their forces more generously than the entire German army possessed at that time. Each Allied company maintained continuous radio contact with their battalion headquarters, and every battalion could directly communicate with division command centers. This robust network facilitated seamless coordination and command, which proved crucial during complex operations. Forward artillery observers, operating from advanced positions several kilometers away, could direct fire with remarkable precision, thanks to radios that maintained flawless contact. In contrast, German commanders attempting to coordinate their defenses found their communications increasingly unreliable, often breaking down amidst Allied jamming efforts, continuous artillery fire, and the inherent chaos of combat scenarios. Equipment that had functioned flawlessly during testing and training would frequently fail once subjected to the harsh realities of the battlefield. One common technical issue was the drift of crystal oscillators, which caused frequency shifts that rendered communication impossible during the intense heat of the Norman summer. Battery-powered radios, designed to be portable, often drained their power supplies rapidly because replacement batteries were scarce or unavailable altogether. The sophisticated communication networks that German military doctrine believed were in place simply ceased to operate under combat stress, creating critical gaps in command and control. The situation in Berlin grew increasingly dire as the war progressed. Technical reports pouring into the German capital painted a bleak picture, reflecting the deteriorating state of their electronic warfare capabilities. In August of 1944, Oberingenieur Hermann, who was attached to the War Operations Staff, warned that Germany had already lost the electronic battle. The Allies' extensive jamming systems, radio direction finding equipment, and signals intelligence operations made it possible for them to locate and target German transmissions within minutes. German codes were being broken regularly, frequencies monitored continuously, and enemy troop movements tracked through detailed radio traffic analysis. The final blow to German communications came in the late months of 1944 and early 1945. As Allied bombing campaigns devastated Germany's industrial infrastructure, production of radio equipment ground to a halt. Factories dedicated to manufacturing radios and related components were targeted as strategic military objectives. For instance, the Berlin-based Telefunken plant was destroyed in November of 1944, and the production facilities in Stuttgart, including those manufacturing critical components such as crystals, were repeatedly bombed. The Sudetenland's crystal production plant fell into Soviet hands in January of 1945. By March of the same year, Germany's capacity to produce new radios had been effectively wiped out. While existing equipment continued to operate, it was now maintained under increasingly desperate circumstances. Field technicians, faced with dwindling supplies, were forced to cannibalize parts from damaged sets and improvise repairs using whatever materials they could scavenge. Genuine replacements were no longer available. As a result, when a key piece of communication equipment, such as a headquarters radio or a tank radio, failed, German commanders found themselves completely cut off from their units, unable to relay orders or receive vital information. In the case of armored formations, the breakdown of communication systems often meant that tanks and other vehicles became isolated entities, unable to coordinate with each other or with command structures. This breakdown significantly diminished their battlefield effectiveness and contributed to the overall collapse of German military operations in the face of the relentless Allied advance. Following the cessation of hostilities, the widespread chaos and disarray in the German military logistics system rendered coordinated action among the remaining units practically impossible. Meanwhile, the United States persisted in refining and upgrading their military technology, even as the war drew to its inevitable conclusion. In early 1945, new radio sets were introduced into the American arsenal, boasting significantly extended communication ranges, additional frequency channels, and enhanced reliability and durability, features that would prove crucial in future conflicts. Despite these advancements, production lines operated at maximum capacity not necessarily because the military urgently demanded more radios, but because the vast American industrial complex was so deeply ingrained and efficient that halting production was a complex challenge in itself. By the time victory was achieved in May of that year, American depots had become inundated with surplus radio equipment, so much so that vast quantities of these devices would never see active combat or operational use in wartime scenarios. The decisive moment arrived on the 8th of May, 1945, when Germany formally surrendered unconditionally to the Allied forces. As part of the post-war occupation procedures, authorities systematically catalogued a vast array of captured equipment and documents. Among these were detailed technical intelligence reports generated from regions including Tunisia, Sicily, and Italy. These documents, which had been deemed highly classified by the Germans and carefully concealed within salt mines and underground archives, furnished the Allied investigators with invaluable insights, effectively offering a window into how their own equipment had been scrutinized and understood by the enemy. In the summer of 1945, American technical teams conducting inspections on German military facilities made a startling discovery. The Germans had conducted remarkably thorough examinations of captured American radios. These reports, written with meticulous care and professionalism, provided an honest assessment of the technological differences. They accurately pinpointed the areas where American innovations held clear advantages, while candidly acknowledging German shortcomings in matching American capabilities. One particularly notable document was authored by Oberingenieur Klaus Hermann in April of 1945, as Soviet forces advanced towards Berlin, a report that would ultimately serve as his definitive statement on the technological trajectory of the war. Hermann's analysis concluded that Germany's defeat was, in fact, predestined the moment German engineers first opened a seized American radio in Tunisia. The internal components, such as frequency crystals, the sophisticated automatic circuits, and the modular design, revealed an industrial philosophy rooted in mass production, one that Germany could never emulate with the same level of efficiency. The Americans had effectively industrialized warfare itself, applying principles of large-scale manufacturing to every facet of military hardware, thereby achieving a technological edge that was as much about manufacturing prowess as it was about innovation. He further argued that future conflicts would be determined not solely by the quality of soldiers or the brilliance of tactics, but predominantly by the capacity of nations to produce high-technology equipment on an overwhelming scale. The Germans, although possessing skilled soldiers, competent generals, and sound tactical doctrines, lacked the essential industrial infrastructure to compete with the United States' capacity for mass production. This deficiency was glaringly obvious in even the simplest of components, such as radio crystals, which required precision manufacturing tolerances achievable only through specialized factories, often staffed by young women working diligently in assembly lines capable of producing millions of units annually. In contrast, German laboratories struggled to produce thousands of such components with comparable precision, highlighting the stark difference in industrial capacity. The post-war fate of the German engineers tasked with analyzing captured American technology reflected these harsh realities of the new geopolitical order. Many of these experts, including Klaus Hermann, were recruited by American authorities in 1946. Hermann dedicated the next 2 years to meticulously documenting German radio technology for U.S. intelligence, capturing the intricacies of their innovations and shortcomings alike. Following his work in intelligence, he transitioned to a consultancy role, providing expertise to American electronics firms. His involvement helped these companies understand and adapt the German technological breakthroughs worth preserving, thus contributing to the burgeoning American military-industrial complex. Numerous colleagues of Hermann's followed similar paths, many of whom emigrated to the United States under programs such as Operation Paperclip and comparable initiatives. These operations effectively facilitated a brain drain from Germany, transferring thousands of German scientists, engineers, and technical experts to America, where their knowledge and skills significantly bolstered the technological frontiers of the post-war superpower. This transfer of talent was instrumental in shaping the technological landscape of the subsequent decades and underscored the profound influence of wartime innovation and industrial capacity on the future of global power dynamics. During the tumultuous years of World War II, a significant influx of German scientists and engineers found their way into the United States. They brought with them not only advanced knowledge of German technological innovations but also, more importantly, a deep understanding of the organizational philosophies and manufacturing philosophies that had contributed to Germany's wartime advancements. Their arrival was instrumental in shaping the burgeoning American industrial landscape, as they absorbed and adapted the methods of mass production, streamlined organizational processes, and innovative engineering principles that would eventually prove decisive in the post-war era. In the year of their migration, 1952, a prominent engineer named Herman authored a seminal paper published in the Proceedings of the Institute of Radio Engineers. Titled, Comparative Analysis of German and American Military Radio Design Philosophy from 1939 to 1945, this work offered a detailed, scholarly examination of the contrasting approaches to radio design employed by the two nations during the war. Herman's analysis was rooted in his wartime experiences, particularly his study of captured American radio equipment, which he meticulously documented and analyzed. His paper served as an academic distillation of insights he had earlier shared with the German High Command nearly a decade prior. Herman's observations clearly articulated the fundamental differences between the American and German design philosophies. He explained that American radio design emphasized ease of manufacturing, operational simplicity, and unwavering reliability under a variety of conditions. These priorities often came at the expense of technical sophistication or the optimization of individual components. The American approach aimed at producing equipment that was straightforward to produce on a mass scale, easy for operators to use, and resilient in the field, which proved essential during extended military campaigns. Conversely, Herman noted that German design philosophy was driven by a quest for technical excellence and theoretical perfection. German engineers sought to create components that were as efficient and economical as possible, assuming that highly skilled operators would be capable of compensating for any limitations in the equipment. This approach prioritized sophisticated technology, minimal component use, and the pursuit of the highest possible performance standards. However, such an idealistic and meticulous philosophy was inherently difficult to scale up. It suited smaller production runs and specialized applications better than mass deployment. Herman's paper highlighted that these divergent philosophies reflected broader strategic choices. The American philosophy, with its focus on manufacturability and scalability, was inherently suited to the vast, global deployment of millions of units. In contrast, the German approach, constrained by industrial limitations and resource scarcity, could not easily be expanded to the same magnitude. This analysis did not remain confined to academic circles. It became a foundational text in engineering education and military training, shaping generations of engineers and strategists. The lessons learned from Herman's comparative study influenced the design of equipment for subsequent Cold War conflicts, the race to space, and the rapid development of computers. The insights gained from scrutinizing German engineering innovations and American manufacturing strategies played a decisive role in establishing and maintaining American technological dominance for many decades after the war. By the 1980s, many of the surviving German engineers, those who had participated in technical intelligence during the war, gathered at reunions and historical conferences to share memories and reflect on their experiences. Among them was Klaus Hermann, then in his early 70s, who delivered presentations recounting his work studying captured American radio equipment in regions like Tunisia and Italy. At a notable conference held in Munich in 1986, he displayed photographs of the very first 508 Seychelles rupees radios that his team had examined back in February of 1943. The photographs revealed young German engineers, hunched over open radio cases, carefully measuring circuits, documenting components, and tirelessly trying to decipher the complex internal workings of these American devices. Herman recounted to his audience that the moment they removed the first crystal holder from the radio and discovered 10 precision oscillators installed within a standard tank radio, he realized that Germany had already lost the war. The crystal, a tiny piece of quartz carefully ground to exact specifications, represented a confluence of physics, engineering ingenuity, and industrial capability. While the principle behind it was straightforward, any competent laboratory could produce such a crystal. The challenge lay in manufacturing millions of them to a uniform quality standard, with perfect interchangeability, at a sufficiently low cost to be incorporated into every military radio. Achieving this scale of production required an industrial infrastructure of extraordinary complexity and capacity, an infrastructure that Germany lacked during the war. The industrial system that was built in America between 1941 and 1945, however, did not disappear after the conflict's end. Instead, it expanded and evolved at an astonishing pace, giving rise to the development of transistors, integrated circuits, microprocessors, and ultimately the sophisticated computers and communication systems that define the modern technological landscape. The same companies that had established the foundational infrastructure during the war continued to innovate, driving forward the technological revolution that has reshaped every aspect of contemporary life. Technology, painstakingly studied, tested, and replicated by German engineers eager to understand and match American advancements. This tiny crystal, no bigger than a postage stamp, was crafted from meticulously cut quartz and securely housed within a sealed metal enclosure designed to protect its delicate structure. The accompanying plaque detailed that this particular crystal was just one of 10 identical components installed in each standard American tank radio, collectively representing roughly 40 hours of dedicated German research and reverse engineering efforts. This exhibit vividly illustrated how a seemingly insignificant element could embody a complex interplay of technological ingenuity, industrial capacity, and strategic intelligence. The Germans had dedicated substantial resources over many months, approximately 40 hours of intensive analysis, to decode the functionality and manufacturing nuances of this crucial component. Their goal was to understand how the Americans achieved such reliable communication systems in the chaos of wartime, and to adapt these innovations to bolster their own military technology. The story told through this small, unassuming crystal underscored the essential differences that defined technological progress during the war era. It was a testament to the extraordinary lengths to which nations went to gain an edge secured not only through brilliant engineering concepts or tactical brilliance but fundamentally rooted in the capacity to mass-produce reliable, standardized components. The Americans, with their vast industrial base, could produce equipment that was not only effective but also accessible to operators with minimal training, ensuring widespread operational readiness. Conversely, the Germans, despite their formidable engineering talent and sophisticated designs, faced limitations in production capacity, which restricted their ability to scale up complex systems for mass deployment across the forces. The exhibit's narrative made it clear that the disparity was not due to intelligence or a lack of technical skill, Both sides had highly capable engineers and worked diligently to develop effective solutions. Instead, the core difference lay in industrial philosophy and manufacturing philosophy. The Americans prioritized creating systems that were robust, straightforward to operate, and easily produced in large quantities, while the Germans focused on achieving high performance through intricate, finely tuned designs that required substantial expertise to operate and maintain. This divergence reflected broader strategic choices, one geared toward scalability and practical deployment across the vast theaters of a global conflict, the other aimed at precision and maximum performance in specialized roles. The American approach allowed for rapid mass production, ensuring reliable communication for countless tanks, aircraft, and ships, even when operated by personnel with limited training. The German strategy, meanwhile, produced equipment that excelled under ideal conditions but struggled to meet the demands of widespread battlefield application due to industrial constraints. Through the careful juxtaposition of the American 508 Seychelles rupees and the German Fug G5, the exhibit vividly demonstrated how engineering excellence alone does not determine victory. Instead, the capacity to manufacture reliable, standardized systems at scale often proved decisive. The curator's notes emphasized that the purpose of the display was not to elevate one nation's engineering prowess over another but to illuminate the fundamental principles that shaped wartime technological development. Both nations had talented engineers, but their differing industrial philosophies resulted in vastly different outcomes. In essence, the exhibit highlighted that technological superiority in wartime was less about raw ingenuity and more about the ability to produce consistent, reliable systems in large quantities, an insight that profoundly influenced post-war industrial and technological strategies worldwide. The tiny, meticulously crafted crystal encapsulated this story, a microcosm of the relentless pursuit of innovation, driven by strategic necessity and industrial capacity, which ultimately shaped the technological landscape of the modern world. During the Second World War, the United States demonstrated an extraordinary capacity for mass production that was unmatched by any other nation involved in the conflict. They manufactured over 100 million radiocrystals, an astonishing feat of industrial efficiency. To put this into perspective, such an output would have required every German radio technician, working non-stop without pause, to labor for 5 centuries in order to produce the same amount. This staggering figure underscores the scale and speed of American manufacturing efforts during the war years. This particular exhibit, which chronicled the technological and industrial achievements of that era, drew an impressive crowd of more than 200,000 visitors throughout its entire year-long presentation. Many of these visitors were veterans, individuals who had first-hand experience operating the very radio equipment now displayed before them. Their familiarity with the hardware added a layer of personal connection and insight, making the exhibit not just a display of old technology, but a vivid reminder of the critical role such devices played in wartime communication and intelligence. In addition to veterans, numerous visitors included engineers deeply interested in the history of technological development. These professionals sought to understand how innovations evolved under the pressures of war, and how technological advancements influenced military strategies. A smaller but significant group comprised historians studying the industrial dimensions of warfare, aiming to explore how industrial capacity and technological prowess shaped the outcomes of battles and campaigns. All visitors, regardless of their background, left with a more profound appreciation of the crucial link between industry and military success. They gained insights into the concept that the ultimate determinant of wartime victory was not solely tactical brilliance or battlefield heroism but the capacity to produce war materiel on an industrial scale. Klaus Hermann, a prominent figure in this narrative, passed away in 1997 at the age of 84. His obituary, published in the Spectrum magazine of the Institute of Electrical and Electronics Engineers, highlighted his significant contributions to radio technology, his specialized work in technical intelligence during the Second World War, and his enduring post-war efforts. After the war, Herman dedicated himself to assisting American corporations in understanding and leveraging German innovations, playing a vital role in bridging technological gaps. The obituary also drew attention to Herman's lifelong conviction that Germany's defeat was not primarily decided on the battlefield but was instead a consequence of industrial shortcomings. He believed that victory or defeat in war depended more on manufacturing capabilities than on tactical or strategic errors alone. His unwavering stance was that the real battleground was the factory floor, where production workers, rather than soldiers, determined the outcome by how much and how quickly they could produce critical war materials. Herman's extensive collection of papers, which he donated to the Deutsches Museum in Munich, consisted of over 2,000 pages of detailed technical reports, circuit diagrams, specifications for various components, and strategic evaluations. These documents, penned between 1943 and 1945, offered a detailed window into how German technical experts perceived American military equipment and the insights they relayed to the Wehrmacht High Command. They captured the technical assessment and strategic considerations of German engineers during a period when technological superiority was a key element of wartime competition. Among this collection, perhaps the most emotionally charged document was a personal letter penned by Herman himself to his wife in April of 1945, as Berlin was falling to Soviet forces. Having already sent his family to relatives in Bavaria months earlier, Herman remained in Berlin, conducting final technical evaluations until he was ordered to evacuate the city. In his letter, he revealed that he was about to destroy all classified documents and equipment to prevent them from falling into enemy hands, a sobering testament to the chaos surrounding the collapse of Germany's war effort. In his letter, Herman reflected on the 3 years he had spent scrutinizing American equipment, from the earliest 508 Seychelles rupees radar sets used in Tunisia to the latest radar technologies captured in the Ardennes. Every example he examined reinforced a consistent conclusion. The United States possessed not only superior technology but also a fundamentally different approach to warfare, one rooted in industrialization. The Americans had managed to mechanize everything, from radio crystals to entire armies, applying the same mass production principles that had revolutionized industries like automotive manufacturing and appliance production. Herman was careful to clarify that it was not a matter of German technological inferiority. In many fields, German scientists had demonstrated advanced theoretical knowledge that exceeded their American counterparts. However, he emphasized that theoretical excellence alone did not determine the outcome of wars. The decisive factor was the ability to produce vast quantities of war materials rapidly and efficiently. The side that could outproduce its opponent, building more tanks, more aircraft, more radios, and all necessary equipment, would eventually gain the upper hand, regardless of the skill, bravery, or tactical ingenuity of individual soldiers. He concluded his letter with a sobering prediction about the nature of future conflicts. If another war was to occur, he believed it would be even more heavily reliant on industrial capacity than previous conflicts. Victory, he asserted, would go to the nation with the greatest manufacturing prowess, the most advanced and efficient technology, and the industrial infrastructure capable of producing precision components at an unprecedented scale. This insight unders a profound shift in the very nature of warfare itself. They recognized that the true power lay not solely in individual soldiers, tactics, or weaponry, but increasingly in the ability of a nation to produce vast quantities of sophisticated, reliable technology on a massive scale. This realization marked a turning point where military success would depend heavily on industrial capacity and manufacturing prowess, rather than just raw combat skill or strategic ingenuity. Throughout the years of World War II, the United States demonstrated an extraordinary capacity to produce war materiel in unprecedented quantities, establishing an industrial might that set it apart from any other nation. Between the first year of the war and its conclusion, America had shown that it could generate an almost limitless supply of critical components and equipment, including radio crystals, which served as vital elements in communication systems. These crystals were not merely small, precisely crafted pieces of quartz. They were the result of advanced engineering processes that had been refined to enable mass production without sacrificing accuracy or quality. Herman, a keen observer and analyst, believed that no single nation could hope to match this level of industrial output. His conviction was rooted in the understanding that the scale and sophistication of American manufacturing capabilities during the war were fundamentally unmatched in history. Post-war analysis and subsequent events confirmed his hypothesis. The Cold War that followed was essentially a contest of industrial and technological supremacy, where the United States and the Soviet Union vied to outproduce and out-innovate each other in areas such as electronics, computing, and automation. Despite the Soviet Union's vast natural resources and enormous population, it was unable to close the gap in key areas like electronics production, computer technology, or the development of automated manufacturing systems. The disparity that Herman initially identified in the production of radio crystals in 1943 eventually expanded into a broader technological divide encompassing semiconductors, microprocessors, and integrated circuits, components that became the backbone of modern electronics. This widening gap underscored the importance of industrial capacity in determining military and economic dominance. The narrative of German technicians examining captured American radio equipment encapsulates a crucial story about the evolution of modern warfare, specifically, the Industrial Revolution that transformed manufacturing during the Second World War. It highlights a fundamental shift from combat strategies reliant primarily on tactics, training, and individual bravery to a paradigm where victory increasingly depended on a nation's industrial infrastructure, technological sophistication, and manufacturing efficiency. The seemingly simple radio crystals that so fascinated Herman and his colleagues were far from magical. They represented the pinnacle of precision engineering. Yet, their true significance lay in the fact that American industry had mastered the art of mass-producing these tiny components with an incredibly high degree of uniformity. Producing millions of identical radio crystals was a feat never before achieved at such a scale, and it was this capability that laid the groundwork for broader manufacturing advances. This technological and industrial prowess extended well beyond radio crystals and became the foundation for virtually every piece of military equipment the United States produced. It also influenced consumer products, setting standards for quality, consistency, and mass production that would shape American manufacturing long after the war ended. The lessons learned by German engineers, who scrutinized American gear in Tunisia, Sicily, and Italy, were difficult but clear. Possessing the most advanced individual equipment was insignificant if it could not be produced in large quantities reliably. Furthermore, even the most sophisticated technology was of little value if operators could not use it effectively or if manufacturing processes could not deliver consistent results. The realization that theoretical excellence was futile without scalable, reliable production underscored a critical insight. Industrial capacity, when properly organized and managed, could defeat all other technological and tactical advantages. The hard-won lessons that came at the cost of Germany's defeat laid the groundwork for modern manufacturing philosophy. Principles such as designing equipment for ease of production, building quality into every component, training users thoroughly, supporting machinery and systems properly, and scaling production to meet demand became central tenets of this new approach. These principles, initially exemplified by American radio and electronics manufacturing during World War II, now underpin global industry across diverse fields. Ultimately, the story that began with a humble German engineer named Klaus Hermann opening a captured radio case in Tunisia in the early days of 1943 culminated in a profound transformation in how nations prepare for and wage war. That small, precisely engineered piece of quartz, the radio crystal, symbolized the broader industrial revolution in military affairs. It marked the point where victory was no longer solely determined on the battlefield by brute force or tactical brilliance but increasingly by the capacity of factories, supply chains, and production lines to supply the technological backbone of modern armies. The engineers who examined American equipment understood this shift deeply. They saw that modern warfare's true battleground was now the factory floor, where technological innovation and mass production capabilities determined strategic advantage. The rise of the radio crystal as an emblem of this new era signified a fundamental change. Military strength was becoming inseparable from industrial strength, and victory depended on a nation's ability to produce and sustain a relentless flow of advanced technology at an industrial scale. It finally came to pass. The reports produced during that time were far more than mere technical documentation. They encapsulated a profound turning point in the nature of warfare itself. These documents not only detailed specifications and engineering details but also marked the end of one era of conflict and the dawn of a new, more technologically driven age of confrontation. Through careful observation, meticulous analysis, and comprehensive reporting, those involved foresaw how future battles would be fought, revealing insights that would shape military strategy for decades to come. Although their predictions and warnings were largely ignored or dismissed by the authorities in Berlin, this negligence did nothing to diminish the accuracy or significance of their assessments. In the present day, many of the core principles they identified back then, such as the mass production of precision-engineered components, the automation of industrial processes, the standardization of parts for easy interchangeability, and the intentional design for manufacturability, have become the bedrock of every advanced high-technology industry. The journey from the tiny radio crystals ground in American factories during the year of 1943 to the sophisticated microprocessors fabricated in modern Asian semiconductor foundries in the 21st century is a direct line that exemplifies this enduring industrial philosophy. What remains unchanged, despite the tremendous advances in scale and complexity, is this fundamental industrial approach. The only difference now is the magnitude at which these principles are applied. Nearly 80 years ago, German technicians, tasked with testing captured American radio equipment in underground laboratories across occupied Europe, weren't simply inspecting communication devices. They were observing the technological blueprint for future warfare, industrial organization, and societal transformation. Their detailed reports, carefully classified and stored during the war, have since become invaluable historical documents. These records explain not only why Germany was ultimately defeated but also how the capacity to produce industrial-scale military hardware fundamentally determines the outcome of modern conflicts. The core conclusion they drew, expressed in highly technical language yet unmistakably clear in its meaning, was that Germany had attempted to challenge the world's most formidable industrial power, America, with insufficient manufacturing capabilities. The tiny radio crystal, a precisely ground quartz oscillator produced by young girls in American factories, teenagers whose work in the United States contributed to a level of industrial efficiency Germany could never replicate, told the entire story. The lesson was that in industrial warfare, raw industrial capacity is paramount. No tactical skill, technological innovation, or individual bravery can compensate for a lack of mass production capability. This vital understanding, learned by German engineers from their examination of American radio equipment in underground facilities across Europe during wartime, remains highly relevant even today. In an era dominated by microelectronics, satellite communication systems, and computer-controlled weaponry, the fundamental truth persists. The side with superior industrial capacity, able to produce vast quantities of advanced technology, will ultimately prevail. The victorious American forces proved this principle clearly between the years of 1941 and 1945. Since then, the world has continuously adapted to the profound implications of this lesson. The importance of industrial strength in technological warfare has become central to national security strategies worldwide, influencing policies, investments, and technological development on a global scale.